Hey guys, welcome to another video. So in this video we shall continue our exploration for limit problems, and we will be trying to solve as many problems as we can in this section. So we are trying to find out some problems, and before that we would need a few results which we tried to prove. So result that we need to prove for this section is this: limit of x tends to infinity 1 plus 1 by x whole to the power x is equals to e. Okay, so basically what this means is this can also be rewritten in the form limit x tends to 0 1 plus x whole to the power 1 by x is also equals to e. So both of these limits are equivalent, and we would try to use this result in a few cases. So let us see how to actually achieve that. Now this one is a bit more challenging than previous ones because we would start off with something we know as the binomial formula. So binomial expansion. Now what is a binomial expansion? So a plus b whole to the power n, this can be expanded when n is a natural number as follows. Like this. So using this we can also find out this expression right here, that 1 plus 1 by x whole to the power x expression, where we know that x is a real number, but for the time being we can actually find out something about it. Like this is also valid for rational numbers and real numbers, but just that we have not done that yet. But we can still use this to find like this, but it would be an infinite series because of the x here. It should be x ck into 1 is irrelevant, so 1 by x whole to the power k, right? Now the thing that is to be noted is this term here. If you just write it as a function of both k and x, it can be written as x ck into 1 by x to the power k, right? Now how to define this binomial coefficient in terms of rational numbers or real numbers or even negative numbers? So there is a definition. It is same as the one that you define with natural numbers, but just that you do not do the factorial thing here, because factorial makes no sense, right? Because you cannot really find out 0.5 factorial because it doesn't go back to 1. Factorial means that you multiply the integers consecutively until you get 1. But in case of real numbers, in case of rational numbers, that's not how it makes sense. Okay, so what makes sense is this: xck can be written as x into x minus 1 into x minus 2 and all the way up to x minus k plus 1 divided by k factorial. This is the expression, and you have a x to the power k extra in the denominator, which gives us the expression for this. And we are literally trying to find the limit of this expression right here, right? So one of the x's can be cut off obviously, and what we do get is this: x by x into x minus 1 by x into x minus 2 by x and all the way up to x minus k plus 1 by x, and then there is a 1 by k factorial. And now there are k terms, so I have divided all the k x's in as denominator to this one. So this gives us 1 minus 0 by x into 1 minus 1 by x and all the way up to 1 minus k minus 1 by x whole divided by k factorial, right? which can be written in the product form as follows: summation r equals to 0 to k minus 1 1 minus r by x, and there is a 1 by k factorial outside, right? Now this definition gives us the notation for factorials, and it can be proved in later sections when we will be discussing about infinite series and infinite products, that this product right here is equal to 1 by k factorial when you put the limit, of course. So when you put the limit, this product is equal to 1 by k factorial into ek factorial, which gives you answer as e. But this product can be evaluated in multiple ways actually, because this product right here has an integral form as well as a differential form, and using the methods of Riemann integration, a lot of times infinite limits can be evaluated, which we shall learn when we get to the integration section, or maybe we can have a glimpse of what's happening, but for now this should work. So this is the basic proof. Now let us do some examples. Example 1: find the limit of sin x by x as x goes to infinity. So basically what we are asking to find is, we can denote the limit by L. So denote the limit by L, and L would be equal to limit x tends to infinity sine of x by x. Okay, now how do we do this? Now this cannot be done because obviously you remember a quite close one where x tends to 0 was given, and if x was going to 0 we knew that sin x by x approaches 1. But here the case is a bit different, and we can clearly see the denominator x, as x goes on to become larger and larger, the denominator becomes much larger, right? And the number should be decreasing by then, the limit value should decrease a lot. But doesn't sin x also increase? No, it doesn't, because we know that sin x for every real value of x lies in the closed interval -1 to 1 for all x belongs to real, right? So this is a property of sin x, that sin x is bounded. Then we can see that sin x is greater than equal to -1, then sin x by x should be greater than equal to -1 by x. Similarly, sin x is less than equals to 1, then sin x by x should be less than equals to 1 by x, right? It is evident that limit x tends to infinity 1 by x is equals to limit x tends to infinity -1 by x is equals to 0. So both the limits actually go to 0 irrespective of the sign, and also since we can bound the function sin x by x using this as we have done here, so we can basically write -1 by x less than equals to sin x by x less than equals to 1 by x, right? Now I'm going to quote a theorem here. It's called the sandwich theorem. It's called the sandwich theorem. It says that if fx gx, hx are continuous functions then if fx is less than equals to gx is less than equals to hx and limit x tends to a fx equals to limit x tends to a hx, and both of them are equal to some alpha where alpha is a real number, then the sandwich theorem states that then limit of x tends to a g of x must also be alpha. So this is the sandwich theorem. That is, the function g of x has been sandwiched in between the functions fx and hx. Okay, so hx is the upper bound for the function, fx is the lower bound for the function, and it is given that the function fx and the function hx, both of them go to some real number alpha when x tends to the value a. So both sides of the limits in which the function gx is sandwiched goes to the same real number alpha, which means that the function in between must also go to alpha, otherwise the inequality would be violated. There is a whole proof for this, but we are not really going to do the proof right now because of the complications, because we need to know what is an epsilon delta definition of a limit. This is completely an analysis course, so I'm not going to code analysis right now unless we need it when we go to the further chapters in probability. So using this we can see that since equals to 0, we can say that limit x tends to infinity sin x upon x must also be 0, since minus 1 by x less than equals to sin x by x less than equals to 1 by x. Since sin x by x is basically sandwiched between minus 1 by x and plus 1 by x, so that would actually solve this problem. So as I said, this is not like a regular problem, but problems like this would be very much evident. Okay, for the next problem I would need a footnote here, that is the footnote of a derivative of a function fx. So derivative of x f of x at x equals to a is defined as, I'll give you the formal definition of derivative for here, and we are going to revisit it when we start derivative, but for this problem this much information is sufficient to do the problem. So f dash a is basically equal to limit x tends to a f of x minus f of a by x minus a. So this basically is the definition of derivative. Okay, this limit, the value of this limit gives you the answer to f dash a. Now the problem, given f of a equals to 2, f dash a equals to 1, g of a equals to minus 1, g dash a equals to 2, then find limit x tends to a g of x into f of a minus g of a into f of x divided by x minus a. So consider the problem. We are given that f and g are two functions which are first time at least once differentiable at the point a, and it is given that f of a is 2, g of a is minus 1, while f dash a, which means the derivative of the function at the point a of f is 1, while g dash a is 2, right? So g dash a is 2 doesn't mean that the derivative of g is 2, it rather means that the derivative of g at the point x equals to a equals to 2. So don't be confused with the definitions and the terminologies I'm using, because it's important that you understand them distinctively. Now limit x tends to a, g of x into f of a minus g of a into f of x. What we are going to do here is something like this. We are going to add and subtract ga fa. Minus g of a into f of x, and we are going to draw a line x minus a. Now why did we do that? Because we are going to separate this first two terms and this last two terms and write them as a separate limit. You will see why. Because we want to really find out how to evaluate this kind of problems using all the information given in the problem, and whatever we just learned a bit ago about the definition of a derivative, which you can see here, this would be handy here. So this becomes g of a into f of a divided by x minus a, plus another limit x tends to a, g of a into f of a minus g of a into f of x divided by x minus a, right? Now what we can do is we can take the constant common, which is f of a, from the numerator, and we can write this as f of a into limit x tends to a, g of x minus g of a by x minus a. Similarly, we can take minus ga common here, and we can write limit x tends to a, f of x minus f of a by x minus a. Now if you remember, this was the definition for the derivative of the function at point a, right? So f of a into g dash a minus g of a into f dash a. This would complete the derivative section for this one, and now it's just a matter to put the value. So f a is 2 and g a is minus 1 and g prime a is 2, so first two terms are 2 into 2. So this gives us the value of 5. So this would actually solve this problem, but as I said, you would need this definition. So once you learn the derivative section, I do not think this would be any more required, but these are the basic things that you should know. Okay, let's move on to the next problem. So we are given to find the following limit. Okay, so this is the problem that we need to find. Limit x tends to infinity, and in the numerator we have root over of x square plus a square minus root over of x square plus b square whole divided by root over of x square plus c square minus root over x square plus d square. Now to do this kind of problems, we, as I said, we need to first rationalize. So let us begin the process. Let this be L. So this is equal to so we shall multiply by this x square plus a square minus x square plus b square into root over x square plus a square plus root over x square plus b square. So this was multiplied, and also we need to multiply by the conjugate of the other term, which is x square plus c square plus x square plus d square. You will see why I did that, because we would need that here. So this thing, first we write whatever there is in the question, x square plus c square minus x square plus d square multiplied by x square plus c square plus x square plus d square, and then the extra term of root over x square plus a square plus x square plus b square. Now once we do the formula, because it's a minus b into a plus b, it turns out as follows. It becomes x square plus a square minus x square minus b square into x square plus c square plus x square plus d square over root. Similarly, in the denominator, it becomes x square plus c square minus x square minus d square into root over of x square plus a square plus root over of x square plus d square. Okay, now the x squares get cancelled off in these two expressions, and what we get is this: limit x tends to infinity, a square minus b square by c square minus d square, and now multiplied by root over x square plus a square plus square root of x square plus d square, actually it would be c square, divided by root over of x square plus a square plus root over of x square plus b square. Right? Now we divide up and down by x to get something. So firstly we can take the constant out, and then we can divide up and down by x to get the following: root over x square plus c square plus root over x square plus d square whole by x divided by root over x square plus a square plus root over x square plus b square whole by x. Now this x can be absorbed inside the square root of each term as root over of x square. So once you put the x inside the square root, it becomes by x square, right? So the limit becomes a square minus b square by c square minus d square, limit x tends to infinity. Numerator becomes root over of 1 plus c square by x square plus root over 1 plus d square by x square divided by root over 1 plus a square by x square plus root over 1 plus b square by x square. Now since we know that this individual term c square by x square, d square by x square, a square by x square and b square by x square go to 0 as x tends to infinity, the answer simply becomes a square minus b square by c square minus d square into root 1 plus root 1 by root 1 plus root 1. This is essentially 1, so the answer is a square minus b square by c square minus d squared. So this becomes the answer. So as you see, some of these problems are a bit challenging than before, because you might have to do a lot of calculations and you have to be very careful, and then again you need to know the method to do all of them. But if you have learned the third chapter completely, if you know how to rationalize and you do not actually make like imminent errors, I do not think you would be getting this wrong. You might be getting this right every time you attempt it. But the only two problems that were very different with this: first, we used the sandwich theorem to evaluate a limit for the first time. So this is a technique which you are not going to forget now. So you can try it whenever you are stuck at a problem. You can try to bound that function and see if both the bounds yield you the same result at the limiting value of the required function. Then the function itself would be that value. And then again, we learned about the derivative of a function and at a certain point, and the definition of it. It is called the derivative from first principle when we evaluate it by the limiting definition, and using that we have solved a pretty good problem, I would say. So these three problems laid a lot of foundation to a lot of things, and in the next chapters we would also try to continue this and slowly introduce the concept of derivative and do problems on derivative directly. Okay, so I think that would be it for this video. I'll see you in the next video, and do not forget to check about the Breatter app in the description. It's a mathematical app where you can find all the video solutions and the theory related to what I'm teaching here. So thank you.